Hello, everybody. Good day and welcome to this session in which we will talk about transformer testing, power transformer testing. My name is Andrej Šepčić. I'm a regional sales manager. I work for Altanova, a global company, and today we will be going through the basic and advanced test which you can do on a power transformer. Just for the beginning, I wanted to say hello to you. I have my camera on, but I will turn it off in order to make this, let's say, more smooth. Please keep in mind we have a lot to cover today. The presentation which you will see, you will be able to receive tomorrow. And in the meantime, I encourage you to ask questions, which I will check at the end of the presentation if we will have time. Having said that, I'm going to check out now, or I'm going to close my camera feed, and I'm going to start with presentation. By the way, I hope all of you can hear me, so let's start. Let me just tell you that today I will use equally the names transformer, power transformer, or PT. When I say that, I mean a big transformer, which I differentiate from an instrument transformer, and everything I will be telling you today can be applied to a distribution transformer or to a transmission transformer. So let's start. Of course, a standard introduction. Altanova, a global company, provides diagnostic solutions to utilities and industries to improve the performance of their electrical assets through portable design equipment, advanced monitoring systems, and professional services. Now, there is a long history of Altanova, and let me just say that we started in 1938, and then from 1999, when TechImp was born, in 2017, ESA and TechImp joined forces. In 2019, Intellisaw joined Altanova Group, and then in 2021, Altanova Group became part of ESCO Technology Group and joined a Doble engineering company. Now, Doble has a very, very long history, and they are a market leader in North America. They're especially known for their power factor, or as we will call it today, 10 delta testing, also the sweep frequency response analysis, and many, many tests of oil. We will hear about it today. We will show some of the devices. In the whole group, we have a lot of more than 150 employees, actually much more than 150 employees, many customers globally. And exactly what we do is we produce testing equipment. We also produce continuous monitoring equipment, and we offer professional services, testing services, also commissioning services. We produce testing equipment and monitoring equipment and provide services for power transformers, circuit breakers, high voltage gas insulated switch gears, cables, medium and low voltage switch gears, batteries, instrument transformers, protective relays, meters and transducers, rotating machines, variable speed drives, and overhead lines. Basically everything you will find in electrical industry. So let's start with the transformer. In order to talk about the transformer, I need to first cover the basis. What is a transformer? What parts of the transformer do we have? So let's first say that in 1830, Michael Faraday and Joseph Henry were the ones who understood that there is something we call the induction. So when the magnetic field changes its strength, it induces electrical voltage in a wire, in a conductor, and that is the main principle used in transformers today. So transformer is a device that transfers electrical energy from one circuit to another through inductively coupled inductors, so the transformers coils. We have coils, we have the primary and the secondary. Sometimes we can have more tertiary coils, for example, and the current, so we apply voltage, let's say on the primary side, the current goes through this coil, it creates a magnetic flux. Magnetic flux it's what couples the primary and the secondary side, and this magnetic flux induces voltage in the secondary side, and when we connect here a load, the current will flow. So why do we use a transformer? Well, we use it to transfer the electric power from one circuit to another. without any change in frequency using the principle of electromagnetic induction. And of course, the two electrical circuits are linked by mutual induction, as we said before. This core, which you can see here, as well as the primary and the secondary side, we will mention later. We have a step up and the step down voltage. Step up transformers will be used in power plants because it will increase the voltage, and step down transformer will be used near urban areas to decrease the voltage. The transformers are used because we have the need to transmit power from one place to another, and it is important to mention only the AC current and AC voltage can use the transformer. The DC current cannot use the transformer, and that is one of the reasons why Tesla won against Edison in the war of currents or voltages. So in short, we would have here let me just use a laser pointer. We would have a generation where we would have a step-up transformer, then we would have transmission lines, and then as we approach the urban area, we would have a step-down transformer, and then another step-down transformer. So we have generation, transmission, and distribution. So basically, when you look at it, even though it seems that you have electrons running from the generator to the load, you don't actually, because the transformers are physically dividing the circuits, the networks, and thus you don't have the physical, let's say, continuity of the wire. What are the transformers' main parts? Core, winding and insulation system, tap changer or on-load tap changer or OLTC, a tank where everything is inside, where everything is contained, bushings, radiator, pressure relief valves, conservator, breather, marshalling box, buckles relay, oil surge relay, and temperature indicator. There might be some other, but these are the main and the principal ones. So transformer core, let's start with the first one. The role of the magnetic core is to increase and concentrate the magnetic flux that links the primary and secondary coils, and it is made of laminations, which are insulated one from each other by oxide coating in order to reduce the losses, in order to reduce the eddy currents. Now, moving on, the core, as you can see here, is made, one could say it looks like two windows, but you can see that effectively these are laminations. So the core is the backbone of the transformer from magnetic and mechanical aspect. It holds the transformer, and the windings are wound around these parts of this one and this one of the core. So it supports the windings. It needs to have low losses, better heat dissipation, and low vibrations. The sound you hear when you approach the transformer, the sound is the sound if these are not very well tight, if they're not pressed together. Now, the next thing would be windings and insulation system. So after you have created your core, you need to wind something around the core. So windings are made of copper material, wound concentratedly around the core limbs, and low voltage winding is usually near the core, and the high voltage winding is above the low voltage winding. They're all separated by pressboard and paper and oil in order to insulate one from each other. Moving on, you can see on your right side some examples. So you need to have a very, very good paper, which is a very good insulator in order to insulate correctly. So when you are winding that, when you're making that winding, you have special machines which are used for that. You can see one example of that right here. Apart from windings, we also have a tap changer, which is responsible to supply a desired voltage to the load. So for example, sometimes if the load is very low, the voltage may go too high, so we would want to reduce that. So we would play with the tap, as we call it. So the tap changer, it's a voltage regulator. Of course, if the voltage is too high, then we can also work on that and change the position of the tap. The tap changer is important because it is the only mechanical movable part of the transformer, and it's seen quite often that it can break because it moves. There are two types of tap changers, the de-energized tap changer and the on-load tap changer. The de-energized tap changer you will mostly find on the distribution transformer, while the on-load tap changer is more frequent on the transmission transformers. And also it is, well, it's not a rule, but very often you will find the tap changer on the primary side of the transformer if we talk about step down, because it is a lower current on the primary side and it's easier to handle the change of a lower current. Every tap changer has a diverter switch and a tap selector, and when you will be able to download this presentation, you can go into this a little bit more deeper. In general, we will show you how we test this afterwards. Here are some examples of a selector switch with a roller contact and a diverter switch contact. What is important to notice is that here on these contacts, after a lot of movements, change of the positions, you can get some, let's say, patina, like it can, well, become dirty, and then the resistance can increase. So that's one thing we will measure. So this should be nice and clean, but it's not always like that. That's the reason why sometimes the tap changer needs to be clean. So when in the context of the whole transformers, this would be 3 windings, phases A, B, and C. The ones you see are high voltage, the low voltage are inside, and the thing you see below and above is the core, and this is the tap changer, which you can see here. Tank is another very important part, of course, of the transformer, because the tank holds everything. It's made from steel, and it supports and encloses various parts of the transformer. It should be strong, sturdy, and free from vibrations. It should also withstand mechanical load during handling, and also vacuum test and pressure test. Tank should cover supports, tap changers, and other fitments. And in general, it should be very, very robust. So you see here one transformer ready to be transported. Apart from tank, we have bushings. So bushing is designed to withstand a very big electrical field, because the bushing is kind of an interface between the transformer and the outside world. And apart from on-load tap changer, bushing is also very much prone to some defects, because it needs to sustain a very, very high fields, since it's basically getting a high voltage into the transformer. You can always understand the difference between the high and the low voltage bushings, because the high voltage bushings are physically bigger than the low voltage bushings, and in the transmission transformer they will be much further apart from each other. Now here are some examples of bushings. They can be made from porcelain or silicon. There are all kinds of bushings, and you can see also some important aspects of bushing. One important aspect is this test tapping or test adapter or tap adapter. This will be used for some of the tests which we will be describing in the past. So this is in the bottom of your bushing. Now, just to let you know, if somebody was curious why these look like little mushrooms or ribs, well, they look like this basically to reduce the leakage current, and also to when it's raining, to kind of have one part dry, because if the rain is falling in from this direction, the below part will be dry, which will definitely reduce the leakage current. Apart from bushings, we have the radiator, a very important part which is used to cool down the transformer. As the transformer works, it is super efficient, but it's not ideal. Some of the energy which goes into the transformer is transformed into heat, and that heat needs to be dissipated. So we use radiators to dissipate that heat. The radiators can be in a form of ribs on the transformer or on the tank itself, or they can be separate, like this one, for transformers which have very big powers. Effectively, you might say that the cooling or the radiator can very much define the power that the transformer can sustain. And then we have some valves, some pressure relief valves. If the pressure inside of the transformer gets too high, this will react and release the extra pressure into the atmosphere. We also have the conservator. It is this thing over here, you can see. So when the pressure increases and the volume is higher, is bigger, some of the oil goes into the conservator. In the normal situation, this is up to like 50% full. And we also have a breather. So the transformer breathes during the night when it's not working, or when it's working less. the volume of the oil is smaller. During the day, when the transformer is functioning more, it is hotter, then the oil expands. So it's bigger, smaller, bigger, smaller, bigger, day by day. It basically breathes like lungs. So all the air which enters the transformer enters through this silica gel, through the breathers, and the breathers have different philosophies regarding color. So in this case, you see the blue one means that it's okay, and the white one means that it's starting to degrade. So it's starting to become too wet. So there are different approaches. That depends on which part of the world you're situated. We have the marshalling box, which is a box which basically controls your power transformers. All protection, let's say, is connected through this marshalling box. And then we have a Buchholz relay, which will detect if there has been a fault in the transformer and if the oil starts to foam. It will trip its protection, and both circuit breaker and the circuit breaker supplying the transformer will trip. Here we have a more detailed design and presenting the Buchholz relays, which I'm sure you'll have time to check later. And we have also an oil surge relay, an additional element to protect the transformer from failure. Talking about failure, that is something inevitable if the transformer is not taken care of. And it is exactly what we would like to avoid by properly maintaining the power transformer in good health. Now, important questions to ask ourselves is why test the transformer? When should we test the transformer? Who should test the transformer, and what tests should we do? So this is going to be the focus of today's presentation. So why? First of all, because the transformer is expensive and because it's usually reliable and durable, but faults can occur sometimes, and not quite often it can be difficult to diagnose the problem with the transformer. The maintenance and visual inspections have some limited value, so we have the basic tests and we have advanced tests. The most basic test, of course, is the visual inspection. Often it's uneconomic to repair a transformer, and the failures of the transformer can be catastrophic, apart from the fact that it can damage, it can start a fire, it can also, heaven forbid, hurt somebody if it explodes. But if you are without a transformer, you cannot supply power to a certain part of your country, state, city, or part of the city. So we need to we need to involve appropriate monitoring and management policies. So some views on testing. Very often we hear, we don't have any problems, so we don't do any testing. But the problem is that when we get a failure, the first question the boss asks is, when was it last tested? So it is important to maintain your transformer the same way, for example, like it's important to maintain the good health of your body, because we are all happy when we are healthy, but we start to focus on our issues when we start having issues with our health. The same can be applied for a transformer. And this policy, if it ain't broke, don't fix it, is not actually correct, because once we start getting slightly broken, it might be much more difficult to fix it. Let me put it like this. If you know when something might fail, at least you can plan an outage instead of being forced into an outage. This is an interesting chart which will tell you how to decide when or what to do with the transformer. If everything is okay with the transformer, which in 90% of the case is, then we don't have to do anything else. But if it's not okay, which is in only 10% of the cases, we have to check whether this is serious or not. If it's not, we don't have to do anything else. But if it is, then we have to do something. So this is the most basic algorithm to help you understand what and when should you do it. In general, let's say one rule which we saw accepted throughout the world is that a transformer, if everything is okay with it, needs to be tested every 3 to 5 years. So this, if you can see, is a situation where a transformer is being tested more or less visually, but you can see that the whole tank has been removed, so whole part of the tank has been removed because obviously something is wrong with the transformer. So in order not to have a situation like this, excuse me, let's first answer the question, who should do the testing? First, university researchers, test equipment manufacturers, transformer manufacturers, utility maintenance personnel, and service companies. And last two are the ones who should do most of the tests. And these are the tests which should be done and which we will cover today. Ratio and vector group. We will talk about winding resistance and dynamic resistance. We will talk about no load, or as they call it also, excitation current, and about short circuit impedance, also known as leakage reactance, and frequency response to stray losses. We will mention insulation resistance using DC method, and tan delta, or also known as power factor, and CNDF, or dissipation factor, and AC method. And inside that, we will also discuss the tip up and tip down test with variable frequency. We will talk about an SFRA test, sweep frequency response analysis, partial discharge test, and oil tests, DGA, and breakdown voltage. So you can see for yourself that it's a very long list of tests. So let's start. Transformer turn ratio is defined as the ratio of the number of turns of wires in the primary winding to the number of turns of wire in the secondary winding. We can see here that this test can identify shorter turns or open turns, and it provides us an information if there is some insulation failure between turns, and it also helps us to understand the vector group of the transformer. In order to do such a test, you can use a single function or a multifunction test set, in this case STS 5000 or M7100, which you can see here, and you would need to generate a voltage on the primary side. Always generate on the primary side and measure on the secondary side, because that way, excuse me, you don't need a device to measure very high voltages. If you were to generate on the secondary side and measure on the primary, we would need to have a voltmeter which could measure up to a few kilovolts. So important thing is that the applied voltage must not exceed the rated voltage of the transformer, always on the high voltage side, as we mentioned, and also we must not exceed the measurement input of the voltmeter. That also needs to be taken into consideration, and the test needs to be done on all taps. So if we have a single phase transformer, we will generate on the primary and measure on the secondary side, like we see here, for example. And if we have an auto transformer, we will do our test as shown in this slide. As we do a test on all positions of tap changer, we should obtain a result like this. So for positions 1 to 11 in this case. If we have a three-phase transformer, we need to do this test for each phase and for each position of tap changer. And on a three-phase transformer like this, we will connect the source on the primary and measurement on the secondary side. If we have a YY, and if we have a Y delta, it will look, or YN delta, it will look something like this. In order to do the test, it is very helpful if you can have a switch box. So in this case, we have with the STS, for example, we have a switch box which needs to be connected to the device, but M7100, for example, will have an integrated switch box, and this is a much faster way to do the test, because this can also control the position of your tap changer, and it can also switch phases between each other, and that way you can obtain results much quicker. And here is one example. We did a test on a 400 kV transformer, and we can see here the nominal ratio 2.795, and we have here the result 2.669, 2.7, 2.7, and the error of 0.21 to 0.43. Now, how do we know if we have good result? The error should be lower than 0.5%, the error between the nominal value and the measured value of the ratio. And Mr. Einstein here tells us also that we can observe this parameter here. So this is the generated voltage and the generated current. The current which we generate is actually a no-load current, but we will talk about the no-load test a little bit later. Here we have another example where we also did the test, and we have the values slightly above 0.5. 0.6, 0.63. So these are the errors above 0.5. What is important to mention, and this is generally a rule when we come to transformer testing, I will mention some numbers today, like 0.5%, 2%, 3%, 1%. If we are slightly above this number, it doesn't mean that we need to change that transformer right away. What we need to do is we need to follow that parameter, maybe do tests more often, and definitely do more tests. So this transformer doesn't need to be changed, because we see that on some positions of tap changer we have some issues, but other positions show us good results. We also can do, what we can also do is we can do a vector group test. So all transformers have a vector group. Vector group is used excuse me, for a successful so that we can do a successful parallel operation of transformers. So for example, DYN11 would mean that the first number D denotes that we have a delta primary winding, and YN denotes that we have a star with neutral secondary winding. 11 is the number, it is a phase shift. Actually, it's this number multiplied with 30 degrees, which will tell us the phase shift between the primary and the secondary. With our devices, you can do two tests to identify the vector group. In both cases, we are generating on the primary side between phases A and B with the B and C short-circuited, and we are measuring in our first test between phases A and B, and in the second test between phases A and C, and we obtain the vector group of our transformer, which needs to be exactly like the one which is written on the nameplate of the transformer. Now the next test will be a winding resistance test. A winding resistance test is important because with this test, we can understand if we have some loose contacts inside. Usually, when we do maintenance, that's what we are looking for. There are some other reasons. What is also important to say is that this is usually the last test we do. And after this test is done, the demagnetization needs to be executed. And also don't do an SFRA test or a no load test after the winding resistance test, because the core will be magnetized, and because of that you may get different results. Important thing to emphasize in this test is that we are generating DC current. That's important to emphasize. That's why we call it winding resistance, not winding impedance. So DC current is being generated, and we are measuring the voltage drop. Now, since the voltage drop depends on the resistance, this is the current we are generating on the resistance, but we can see that in this equation there is also the inductance. We want this part L di dt to become zero so that we can measure the resistance. That's why in some cases the measurement of a single phase on a single position of tap changer can be 2, 3, 4 minutes, depending on how big the transformer is. And when we measure for a star connected winding, the resistance measured is between line and neutral, and for delta is between two phases. If we have auto transformers, the resistance of high voltage side is measured between high and low voltage, and then the low voltage is measured between low voltage and neutral. We also need to use the temperature compensation, because very often when we will be evaluating the results, we will see the numbers which are obtained in the factory at a much higher temperature, usually 65, 70, 75, 80, 85, depending on the producer. And we are measuring right now, and it's maybe 15 or 5 or 25 degrees. So our test sets have that automatic temperature compensation. So we can see here that in time, the voltage will stabilize. The current will actually reach the desired value. We need to wait until di dt becomes zero so that we can measure R. And this is how we would connect. We would generate a current and measure a voltage drop. And in doing so, we would be able to do that step by step. So single phase or with a switch box. Once again, we can use a M7, which has an integrated switch box, or STS, which has an external switch box, because the switch box will make testing up to 70%, 60 to 70% faster. The reason why this is so is because when we use a switch box, we need to energize each phase only once and de-energize only once. And if we don't have this, we need to energize and de-energize for each position of tap changer. So if we have 20 positions of tap changer, there is a big difference between 3 energizations and 3 de-energizations, and between 60 energizations and 60 de-energizations. So in that respect, always, if I can suggest, go for an automatic device with switch box. Here are some results. When we measure, of course, we measure on the primary and the secondary side, all positions of tap changer, all phases. And in this case, we see quite high resistance on the primary side because the primary side has lower current, it can have a higher resistance, 36.7 ohm, while in our next case, we can see that the resistance is much smaller, 0.63 ohm. So this is much smaller. So this is like 70 times smaller, almost. And we can also see the columns measured value and compensated value because, for example, right now it's 25 degrees, and I'm comparing this to the result, which was obtained at 40 degrees. Now, another thing to take into account is a graphical representation of the results, and this is how this would look like when you do few positions, well, more than few, 11 positions on a tap changer. And we also need to keep in mind that if we don't have the values from the factory, we can always compare phases. So the key thing is the difference between phases cannot be more than 2%. In some cases, maybe 3%. And that also applies to the comparison with the nominal values. The difference cannot be more than 2 to 3% from the nominal values. Now, if we measure the resistance, not only when the tap changer or energized or de-energized tap changer is still, but if we want to measure the resistance while the tap changer moves, then we will do a dynamic resistance of on-load tap changer. We already spoke about tap changer, and as the tap changer moves from position 1 all the way to position 4, it creates this specific form. If you measure the resistance for every change of tap changer, you will obtain a graph like this. And each graph should be the same from each position. If they differ, and what we measure is the ripple, which you can see here, and the slope is if these numbers differ one from each other, then we should look into this tap changer a little bit more. So dynamic resistance of on-load tap changer. If we talk about just static resistance, we measure all internal contacts and the winding resistance, so the resistance of the winding. But if we do a dynamic resistance, we also get the information of the movement of the diverter switch. So this is why we do it. This is why it's useful. It is not used in all countries of the world, but in many countries, this is a standardized test. The next test we're going to talk about is the no-load test or excitation curve test. It's one of the tests that allow us to find out the parameters of our transformer. So this test will show us the losses in the core. Basically, what we need to do is generate voltage on the primary side with the secondary side open. That's the only thing we need to do. This test will show us abnormal core grounds, winding faults, on-load tap changer problems, and manufacturing defects as well. And as I said, determine the losses in the core. So this is something where we have to generate on the primary side and basically measure the current, which is the current which magnetizes the core. So the transformer, if it wants to work, if it wants to function, it needs to magnetize the core. Having said that, I need to emphasize that in some countries it's done vice versa. So we are generating on the secondary side with the primary side open. Essentially, there is not much difference. It's just that we need to multiply that result with the TTR number, the transformer ratio of our transformer. In case we have some fault, let's say that these two windings are short-circuited, there will be a higher current getting into the transformer, and this will show that we have an issue with our transformer. Also, the way how we should evaluate the results, before evaluation, this is how we do the execution of the test. We connect the primary side with the secondary side open, and we generate the highest possible voltage. Usually, if we cannot generate up to 10 kilovolts, then we need to recalculate, and our devices can do that. What is important is the evaluation of the result. Usually, the middle phase will be have lower values because it's in the middle. It has lower losses in comparison to phases A and C, which are on the sides and at the beginning and at the end of the transformer, and have higher losses. So let's see what Mr. Einstein has to say. It says for this test comparison of the results, we have to take into account the fact that when this test is done in the factory, it's done with the true three-phase, and we are always getting the different numbers if we compare with the testing in the field. That's why we cannot actually compare with the results from the factory. We need to compare and see if, let's say, the results we did today are different from the results we did last time when we did the test, and we also compare the phases. Short circuit impedance is the percentage of the nominal primary side voltage required to circulate full load current under short circuit conditions of the secondary side, or the percentage impedance of the transformer that is a full drop load due to the winding resistance and leakage reactance expressed as a percentage of the rated voltage. I can put it like this. You have copper in your transformer. That copper has resistance. That resistance will cause some losses. We measure the losses in copper with this test. We short circuit the secondary side and increase the voltage on the primary side until we obtain the nominal current on the secondary side. That's the theory. In practice, we don't have to go so high, but this is the number you will find on your transformer's nameplate, and it's marked as Z percentage. So the important thing here, this is like the Einstein says here, that this is like the power which you need to invest while driving a car to move the car, because the car has its mass. Excuse me. This test can show us also if we have some possible winding deformations caused during the transportation. There are some other tests who can do that better, but when we execute that test, we need a source on the primary side, we need to short circuit the secondary side with thick cables, and we need to start increasing the voltage on the primary side. And as we do that, we actually need to perform 3 different tests depending on which method we use, and we will see that in a second. And we need to compare that number with the number on the nameplate. That number can be, let's say, 7.8 or 10 or slightly higher or slightly lower. So that means if the result is 7.8, that if you have a transformer which is 1000 to 100, for example, or let's say that it's 100 on the primary to 10 on the secondary. That means if my Z percentage is 7.8, that I actually need to generate not 100 on the primary to get 10 on the secondary, but 107.8, because 7.8 will be lost in the resistance of the copper. I hope that is clear. And we have 2 methods, 3-phase equivalent and per phase method. We usually use 3-phase equivalent because per phase method is applicable only if we have a star winding with neutral point accessible. In both cases, we do 3 measurements. So this is the example for a 3-phase transformer, 3-phase equivalent method. And this is the formula which we would use to calculate Z percentage. This would be the connection for per phase method. And as we do the test, we get 3 results. And here we see the measured and the nominal value. We have another example in which actually we forgot to punch in the correct nominal value. The correct nominal value was 8.1. We got 8.2. So this is a pretty sweet result. Also, the difference between the nominal and the measured result cannot be more than 3%. Frequency response of stray losses is same like short circuit impedance. And by the way, let me just mention that short circuit impedance test is also called leakage reactance test in the States or some other parts near the States. And if you do short circuit impedance test, not on a nominal frequency, but on a plethora of frequencies, 15, 35, 60, 75, 80, 110, 220, etc., you will get results for FRSL, or frequency response of stray losses. So it is the same like the other one. It's just that this will give us a little bit more information. We will be able to see the influence also of skin effect. So you can see that the connection is the same. We need to compare phases to in order to interpret these results. And in this particular case, we see that one phase, phase B, is not like phases A and C, which will lead us to believe that this transformer might have an increase in eddy currents. So this is the frequency response of stray losses. Now, the next test will be capacitance and tan delta. So capacitance and tan delta is the most common technique used to assess the insulation of the transformer, and it's important to emphasize it is an AC test. With this, we can change the state of the insulation and a possible mechanical deformation. And the good thing is that we can either evaluate the result using the standard, let's say, accepted values, or we can compare to results we obtained previously testing that transformer, or compare to some tests which have been executed in the factory as the transformer when the transformer was produced. The short theory behind this is that we model insulation like a capacitor. Why do we do that? If we have, let's say, 220 to 110 transformer, these are two different potentials, 110 to 20. And if we have an isolator between these two potentials, that's the definition of the capacitor, which we see here. In the capacitor, we see that we have a voltage and the current shifted by 90 degrees, but we know that there is no such thing as an ideal capacitor. We always have a resistance here in parallel, which adds this current. It is a very small current, but it is a measurable current. So long story short, we need to sum in a vectorially these two currents, and we get this total current. And then if we check, this angle delta here is what we are measuring. This angle, if it's bigger than about 0.7 degrees, more or less, we have a problem with our insulation, which leads you to believe that this is very much like a capacitor. So tan delta is IR over IC. Tan delta is also known as dissipation factor. Power factor, on the other side, in the other case, is not IR over IC, but IR, resistive current, over IL, total current. But since this angle is very small, this vector is almost equal to this vector, which effectively means that we're talking about the same parameters. So if this angle is less than 5 degrees, and it should be, then power factor and tan delta have the same values. One of the ways how you can do a test using these test sets is, for example, you can do this test on the body of the transformer or the bushings. In this case, we are connecting to the tap adapter and generating high voltage here on the top and measuring the current here and obtaining a value. All types of transformers can be tested with tan delta test, single phase, three-phase, 2 or 3 winding transformers with or without tertiary, auto transformers, the transformers with delta or star winding. And what we measure are basically on the body 3 capacitances: CH, capacitance between high voltage winding and the ground, and CL, capacitance between the low voltage winding and the ground, and as well as the capacitance between high voltage and low voltage winding. While we measure capacitance, at the same time we measure this phase shift between the voltage which we generate in the current, which is generated by our voltage, and that defines the tan delta or power factor. So what we need to do is to short circuit the primary and the secondary side, and then first generate on the high voltage side and measure CH and CHL, and then shift and generate on the low voltage side and measure CL and again CHL. With double M7100, you don't have to do any changes. You basically connect 2 high voltage outputs, and you can do all this with one setup. If we have tertiary, of course, we have more capacitances which we need to measure: high voltage to ground, low voltage to ground, and tertiary to ground, and everything in between. The good thing about this transformer is that we have, let's say, a better resolution, in a sense that if we have an issue only with one insulation, let's say low voltage to ground, we will see that, because in another test, which we'll see in the end, the DC test, we are just measuring one resistance. Here we measure all kinds of insulation. When I say all kinds, I mean insulations between different points of voltage. This would be some results. So in this case, we generated different voltages, and we obtained different, same capacitances, which is important. You can use M7 or M4 or STS plus TD or TDX to do this type of a test. And you can also, of course, you will do this test on a nominal frequency, and the voltage doesn't need to be more than 12 kilovolts, even though 10 is often more than enough. Why am I saying this? Because somebody can rightfully ask, well, can I test a 400 kV transformer with 12 kilovolts? Yes, you can, because until 10, 12 kilovolts. You don't need more than that to practically for the insulation to have all the molecules inside polarized. So all the polarization is done with 12 kilovolts. If we change the voltage and do so-called tip up or tip down test, which is often performed on rotary machines, our capacitance needs to stay the same. So actually it is. We see that the only difference is that here the capacitance is 320.5 and here is 322. So there is, excuse me, very small change in the capacitance. And we can also have a variable frequency, and this is more or less done quite often on the bushings if they show us some issues with the value that we measure. So here we see that as we increase the frequency, the power factor or tan delta also increased, and this delta, the change of power factor or tan delta, is also defined. So it can change, but not much. It should change a little bit, but not much. We'll skip this because, or let me say that the difference between AC and DC test is that the AC test is less destructive. It is also, so tan delta is less destructive in respect to the so-called polarization index test. It is also time independent because you can get repeatable results with AC test, with DC not often. It is a faster test and it is giving more similar conditions because we are using an AC voltage, which is normally used on our transformers. The DC voltage is not used on transformers. Yeah. Now, moving on, we still have quite a lot to cover and not too much time. So capacitance will provide the information of the deformation of the winding or a partial breakdown of the bushing, while the tan delta will tell us about aging of insulation, possible contamination, moisture increase, insulation. In general, it will show us that we have issues with the insulation. Now, there is another test which is called the DFR, and it's also a tan delta test. I just need to emphasize that the DFR will tell us how much water do we have in our insulation, and it is a tan delta test done on variable frequencies from millihertz to kilohertz. Now you may think that there is no water in the transformer, and there always is, at least a little bit. Now 90% or more is in the paper, in the cellulose, because it's more water absorbent, but there is a limit to that, and with this test you might also determine the amount of water. Now, sweep frequency response analysis is the next test we're going to cover. This test can be done on many assets: power transformer, filters, measurement transformers, and rotary machines. The idea of this is that the transformer is a complex system of resistances, inductances, and capacitances. Now, if we were to generate a small voltage, not a big one, on the primary and measure on the secondary and then do vice versa, we would get a transfer function. So let me show you. You have here resistance of the coil, you have inductance, and you have the parasitic, let's call it the parasitic capacitance between two windings, between the winding and the housing, etc., etc. As you change the frequency from few hertz to few megahertz, you will get a type of a transfer function, which I will show you later. But before that, I will tell you what are the detectable defects. So with this device, with this method, you will, the most important to mention is that this is the best method to understand if something geometrically moved inside the transformer. And this test is always done in a factory, and then the transformer is transported onto the location, and then that test is repeated. If we get the same result, then it means nothing hit the transformer. But you can do this test also very often when, not very often, but after there has been a high current fault near the transformer, because the high current passing through the transformer may cause a big electromagnetic field which can physically move the coil. So you can see axial deformation, radial deformation, partial and localized deformation of a coil, short circuit between turns, breaking with the winding, connection problems, and problems with the magnetic circuit. And you can see all these pictures here. Here we have, let's say, breaking of a winding. Here we have deformation of the winding, and a small device is needed to do this. So In this case, M5500 will generate low voltages. When I say low, not more than 10 volts peak to peak, but in a wide variety of frequencies, and it will generate a result using basically dividing two values, the output value of voltage and the input value of voltage in a logarithmic scale, and then you will get a function like this. How do we interpret the results? So here we can see that these three, so blue, black, and green curves don't completely match. They do match here, but not here, and that means that there is an issue with the transformer, and you will actually get two plots, the amplitude and the phase shift plot. So, excuse me. What we do with this test, actually we obtain something which we call the fingerprint of the transformer, and we get two presentations, graphical representations, as we mentioned before. So this would be the change in amplitude as the frequency changes, and this would be the change in phase as the frequency changes. And we can detect something like this. So you see this bulk on the winding, it wasn't there when it was produced, but the high current passing through the transformer made it happen. You will not be able to see that when you do some other tests, but SFRA will show this very nicely. And there are different ways. This is a radial deformation, and this is an axial deformation. Now, there are many ways, well, not many ways, there are a few standards how to do this, and regretfully, we don't have time for that, so I'm just going to quickly through this, but I'm just going to mention once again that before we do this test, we need to demagnetize the transformer. That means that if we have done the test of winding resistance before this, and then we do the sweep frequency response analysis, we will not get good results. So we need to demagnetize our transformer. And then there are ways how to do this test. So high voltage injection, low voltage side open, or high voltage injection, low voltage side shorted, and then low voltage injection, high voltage side open, and high voltage injections and measurement on the low voltage side. So when we do all these tests, we compare, or actually we just load these results into the software, and the software does the comparison. What is important to say is that it is great if you have the result from the factory, and because then you can compare with the original value. Now, we said that this test should be performed if we had some issues like the transformer fell into the river or there was a lightning hitting the transformer. But what I wanted to tell you is that this graph itself doesn't tell you anything, but when you compare it with the old results, you will see the influence of the core, which is the first part, then interaction between windings, then winding structure influence, and then earthing leads influence. So if everything is okay, let's say here, and something is not okay here, then you know that there is a problem with earthing leads influence. Now we have two more topics to cover, and I think we're quite good with time. We still have 5 more minutes. I hope if I go 5 more minutes over, you will not hold it against me. Partial discharge on the transformer is a huge topic. I'll try to sum it up as quick as possible. So partial discharges are micro sparks inside, and then we could talk about internal PD or on the borders of different insulating materials. So you can have small sparks inside the insulating material or on the borders of two different insulating materials like oil and air, or like XLPE and paper, or XLPE and let's say air. So we have internal and surface PD. We also have corona PD. I'm not mentioning it here because we consider it to be a noise. And in general, you don't want to have any kind of sparks in your insulation. But when you start to have them, you want to understand that you have them and you want to move on with that, to see how strong it is, how repetitive is it, to understand what problems do you have. So it can show you if you have some local overheating in the transformer, if you have paper damage caused by overvoltages or lightning strikes, manufacturing defects, or if some aging processes on the insulation has taken place, or you have contact wear in tap changers, or deposition of conductive species on the transformer board, or faulty bushing taps. All that can be seen with the PD test. So When do we do a PD test? Well, we do it always in the factory after the transformer has been produced, and we also do it in the field. In the field, we can do online or offline test. Online means that we are using the voltage of the network, and offline test means that we have brought a source and we will energize the transformer. Online is much easier to do and much cheaper. Offline has some possibilities which online doesn't have. We can also do a permanent monitoring of the transformer, which is often done if that transformer is important for us. Which sensors do we use and when do we place them? Well, this is one of the sensors. It's called a tap adapter, and it's not bigger than your palm. It's effectively a capacitive coupler. There are different types because they will be put into the tap adapter, which we mentioned before, the one which we used for tan delta or power factor measurement. While these are the acquisition units, which we will use to measure the tan delta, the partial discharge. There are some additional sensors which we will show, but what is important is that after you have done testing, it is very important that you basically must remove the noise. Since you are measuring very, very small values, the devices which are used in this measurement are very, very sensitive. And because of this sensitivity, the noise can mess up the measurement. So with our technology, you can easily remove the noise and separate the sources to understand what are we talking about, because this is one of those measurements where the execution of measurement and obtaining of the results is not so difficult, but interpretation can be tricky if you don't know what are you looking at. So this is where the sensors lie, at the bottom of the bushing. This is where you would connect your acquisition unit, and let's not forget, this is an acquisition unit, this one is called Aquila, and this one is called Micro Aquila, and effectively these are very advanced oscilloscopes with even more advanced software. This would be that advanced software. Now, these are some more examples. Actually, this is an example of a monitoring system which can monitor partial discharge and tan delta at the same time. These are some additional sensors used not so often. So this one will be used if your transformer has a window, and these ones will be used on the grounding leads of your transformers if you cannot connect your tap adapter sensors. If you decide to go for online monitoring, then the whole system will contain a box like this, which will contain an acquisition unit and which will monitor your transformer 24/7. Now, and it will show it to you like this in your SCADA system if your bushings and your transformer has problems with tan delta or partial discharge. One of the last topics, very, very important, is dissolved gas analysis. So dissolved gas analysis very often is the driver for further investigation of the transformer, because transformers, many transformers, not all of them, have oil inside as the cooling liquid, and also as the liquid which isolates inside the transformer. So if the transformer's oil is okay, then also the transformer is okay. But if not, then the transformer also might have issues. So DGA is the first indicator of a problem and can identify deterioration of the insulation, overheating, hotspots, partial discharge present, arcing, and in general, it will tell you about the health of the transformer. So we can say that the oil in the transformer is like blood. So if a human being is feeling bad, they will go to a doctor and the doctor will take out the blood. And then you have loads of parameters which can be read from that blood. Electrolytes, you can read the pH value, you can check the white blood cell count, the red blood cell count. So many parameters can be read from that blood. The same thing, even though it's not the same thing, but we can do many tests with oil. DGA is one of them. DGA means dissolved gas analysis, because when you have a higher temperature in the transformer or partial discharge in the transformer, it will produce gases. The first one produced will be hydrogen. Then you will have methane. Then you will have, let's say, carbon monoxide, ethane, ethylene, acetylene, oxygen, carbon dioxide, nitrogen. These are the most important and basically standardized gases. When I say standardized, there are numbers related to how much of these gases can be in the oil of the transformer. And as I mentioned, the reason why this happens, just a second, I want to show you this first, is because the oil is an organic compound. And when the organic compound is stressed, whether through temperature, high temperature, or through sparks, which is a PD, or through arcing, then this chain will break. And first you will have the hydrogen dropping off, and then you will have the methane and ethane and acetylene and ethylene, etc., etc. And depending on different conditions which you have in your transformer, you will have different gases in your transformer. So if your oil is oxidizing, also if you have an influx of a lot of oxygen, then you will have carbon monoxide, carbon dioxide, and or you will even have water in your transformer, which will show you that you have cellulose degradation. And here you can see at which temperatures which gases start to appear. So, for example, for hydrogen, as the temperature increases, you will have more hydrogen. For methane, as the temperature increases up to a certain level, the amount of methane will increase, but then it will start to decrease. So you see, this is not linear. That's why you will often need a tool to understand what's happening inside of your transformer, and that is something we call a Duval triangle. Also, Roger ratio, Dorenberg method, and key gas method. So what will this tell you? For example, Duval triangle will tell you if you have this much of methane and this much of ethane and this much of hydrogen, you have a problem with heating, for example, overheating, or you have a problem with arcing, or you have a problem with PD. You cannot just take the result and interpret it just by looking at numbers. You need to make relations between gases, and this is what these methods do. And here you can see different possibilities, different possible faults which you can detect inside of your transformer when you are using the DGA method. I will also mention that Doble has the most advanced laboratories in the world, and I've just copy-pasted here some of the tests that can be done in Doble laboratories. There are many of them. Also, Morgan Schaffer laboratories are very, very advanced, and both of these laboratories can provide you with the analysis of oil. You just send your sample, and they can analyze everything in your transformer's oil. I don't think there is no test that we cannot do. So just going through it, all types of oils, because they can be oils or esters, natural esters, etc. We can do all types of tests, like testing the color, appearance, water inside, the dielectric strength, the acidity, the dissipation factor, which is you can also do a tan delta test of the oil, and then you can test all other parameters within your oil. You can test for corrosive sulfur in oil. You can test for, let's see, because the sulfur will make your accessories inside the transformers corrode, and it will degrade the insulation of the transformer, for example. So all these tests can be done. Unfortunately, we don't have time to talk about them. What we do have still time to mention is the breakdown voltage. How do you do a breakdown voltage test? It's one of the most basic tests. You take a sample of the oil, you put it in a standardized holder in a tank, and we apply high voltage with a fixed distance between electrodes. At one point in time, as we increase the voltage between electrodes, the oil will become conductive, and there will be a spark between electrodes. We know that number and see if it's lower than allowed. Of course, excuse me, that number needs to be as low as possible, because we are testing the conductivity or the insulating properties of our oil. Last test I'm going to mention is a DC voltage testing, which is an older method. Today we prefer to use tan delta, so power factor testing using an AC method. Basically what we do, we generate, let's say, 5 kilovolts. And by the way, let me mention that this test really makes sense a lot more sense if we have if we don't have a liquid insulation, if we have a solid insulation, because if we have a liquid insulation, that liquid moves around the transformer, so we don't have a repeatable result. So even if we have the solid insulation, we might have issues with repeatability. Long story short, we're going to do a test which is called polarization index. which is the ratio of megaohms after 10 minutes divided with megaohms after 1 minute. And if that number is, you can see here, less than 1, then we have a dangerously bad insulation. If it's between 10 and 1.1, so 1 and 1.1, it is poor. If it's between 1.1 and 125, questionable, and between 125 and 2, it is fair. Another test, which is called DAR, or dielectric absorption ratio, is almost the same like PI. It's just that the ratio is not 10 minutes versus 1 minute, but it's 30 seconds, 1 minute versus 30 seconds. And also then we get the number and we compare to nominal values. So it's 3:37 where I am, and I want to thank you for your attention. Honestly, it was a lot of things to cover, and I understand that this can be easily broken down into 4 different 1-hour presentations. I just wanted to list the test and give you just some short insights. I'm sure there are many things I haven't mentioned because I didn't have time to go into details, but let me now check if you have any questions so that we can answer them. Let me see, we do have a lot of questions. So what I'm going to do, I'm going to start answering questions, and you can stay with us. If not, then feel free to leave. Thank you for your attention, but let me now start with questions. Okay. Could you send us the video of the recording? You will get the video, don't worry about that. You will also get this presentation. I don't know if we will be able to send you the PowerPoint, but we will definitely be able to send you the PDF. Let me just stop now with presentation, stop showing screen, and I will continue reading the questions. If in a case of a transformer trip at short circuit, just a second, are we recommended? I need to increase this. Some questions. This screen is a little bit small, so that's why I can't see the whole question. So, in case of transformer trip at short circuit, what are the recommended tests? I would first start with the ratio test, then winding resistance, and that will show us something. And then you can do a tan delta or a power factor test. If all these tests prove to be okay, then I would say that we are fine. If not, then you would continue with SFRA. Maybe if you have the basic results, you can, and definitely, I forgot to say, I would also test the oil of your transformer if you had such a situation. Let me see the next. How we calculate the winding value derivations, unbalanced values between phases, delta star. I'm not sure how to answer that question. So how we can calculate the winding value deviations. So if we are talking about the resistance, you will take the nominal value which you have on the nameplate or on the what is called the passport of the transformer, and then you will take the measured value, and the difference shouldn't be more than 2 or 3%, if that was the question. Then the continuance of the question is unbalanced values between phases, delta or star. Please provide us the formula. That is quite specific, so if it's not a problem, my email is asepcic@doble.com. You will see my email, so if it's not a problem, I would really appreciate, Mr. Shair, if you can give me some more insights on your question. Which subcomponents of the transformer creates the most problem? Tap changer, windings, leakage. So that's a good question. I mentioned bushings, tap changer would be the first ones. Then you might have, and then of course oil. But oil is a component. It's not a component which is solid, but it is liquid. But very often oil can be treated. So with oil is often treated because it's expensive in order to provide better insulation. So I would say focusing on bushings and tap changer will be in some cases enough, and also doing oil tests. Then we have a question, can we get PSSI software? Mr. Solomon, I'm not sure what you mean, but feel free to explain further what you mean by PSSI software. Mr. Asfar is asking, can you give us some illustrative calculation for short circuit impedance test of a given transformer? This is not the topic of this discussion. We will have further discussions on the short circuit impedance. In general, I will just say that this is something which is done when the transformer is produced to understand what is the maximum current that the transformer can sustain. So for that reason, let's leave that for the next seminar. Can a vibration or shipping time motion affect the vector group of a given transformer? Well, if it does, then you have a big issue with the transformer. I mean, it can. It means something moved so much, but in general, it shouldn't. If so, how can we check it? Well, you need to do a vector group check and see if it coincides with the one which is written on the nameplate of the transformer. Mr. Asfar is asking, how can we test zero sequence parameters of the transformer? There is a test for that, but there is also, well, you don't need much more than just some voltage and measure in the specific points, but also a topic for another discussion. So we will have more transformer related webinars. So let's leave it for that if it's not a problem. How can I check ratio test of bushing current transformers? Transformers bushing whose middle phase is equipped with CT winding. Okay, so we're talking about embedded CTs. You can check them by using a voltage method. You will generate the voltage on the secondary side and measure the voltage on the primary side, on the bushing. So this is how you will do it. You cannot use a standard current method, but the voltage method. Mr. Fred is saying, I once performed a test on a 100 kV transformer that passed insulation resistance and TTR test, but failed winding resistance with winding results margin slightly above 2%. On loading, the transformer voltage fluctuations was experienced on repeated testing. It failed TTR and passed winding resistance. Kindly advise on such. It is not easy to give you an advice on such a particular situation. I can only say that in Doble there is a team called Transformer Forensics, which can give you a better insight. In order to give you some advice on that, you would need to send me all the necessary data, because this is a little bit generic, so that I wouldn't want to speculate on such an important thing. Marianne is asking, what happens if we do not have the results from the factory of the SFRA test? Is there any way to see if there is a problem? Unfortunately, there is no other way, but the sooner you do the first test, the better, because all the subsequent tests will be compared to that. So if you don't have results, then you start with SFRA today. You can do FRSL test and see if there are some deformations, or short circuit or leakage reactance test to see if there are some deformations. But if not, then we are probably okay. Moving on, let me see. So regarding noise measurements, there is a large variation between IEEE and IEC standards regarding noise level. Which one gives better end results? I have to be honest, I don't know. About the noise, I haven't tested noise on a transformer very much, but I can check, Mr. Petri, and if you send me your email, I can check with the people who know more about transformers than me. Mr. Jumpeng is asking, hi, for SFRA comparison, must the test set to be used in factory at site? Well, the test setup should be the same, the devices not necessarily. So he's saying, for example, factory is using Doble at site. Can I use test set from other OEMs? The method of testing is the same at factory and site. In general, the answer is yes, but the practical problem might be that the format of the files where the results were saved might be different, and that might present a problem. If the format is generic, and you can open it with the new device, then you're fine. If not, then we have an issue. The next question, why the phases were shown 4, 8, 12 in the SCADA screen? Well, that depends. You see, many world is big and it has different notations. Red, yellow, blue, 1, 2, 3, 4, 8, 12. This was probably from a country where this is the notation for the phases. Of course, it's just the nomenclature. You can choose any way you like. The next question is, what is the unit of partial discharge? Is it a coulomb or a millivolt? This is a good question, Mr. Ramados, and the answer is both. Now, the real unit is picocoulomb, but we need to be aware that that can be measured only in a laboratory. We are talking here mostly about testing in the field, where we don't have, according to the IEC 6270 Faraday cage around the transformer. So of course you can always pretend that you're in a laboratory and measuring picocoulombs, but if you do that, you are, I would say, not doing the best that you can. The reason is that when the method IEC 6270 was developed, the electronics used to measure partial discharge were analog and didn't have a lot of capabilities, a lot of possibilities. Today, with the digital electronics, we can do much better. And if we want to do much better, we have to get out of these constraints of the 6270 and measure in millivolts. Because effectively, even if you measure in picocoulombs, what's happening is that your acquisition unit is always measuring millivolts. The first measurement is always millivolts. You don't have a device which directly measures picocoulombs, and then you recalculate to picocoulombs. Now, this recalculation can be an issue because this correlation between measured millivolts and expressed picocoulombs can be linear or not. My suggestion, in the field, millivolts. So the answer is both picocoulombs and millivolts. And I need to mention, in PD testing, it is not just the number of millivolts and picocoulombs. We need to break through this cage of understanding that when we do PD testing, the interpretation is more not just amplitude, but also repetition rate is important. And the most important thing is the type of that PD, because we can have nanocoulombs or coulombs of corona and we couldn't care less. But if we have picocoulombs of internal PD, then it's a pretty big deal. So there's a whole story behind that, and I hope that in the future we can have, let's say, 4 different transformer testing webinars: basic tests, advanced tests, oil testing, and partial discharge testing, so that we can assess properly, so that we can do right when it comes to this. So we have already done, if I'm not mistaken, the PD on the transformer, but now we can also focus on DGA, basic tests like ratio, winding resistance, short circuit impedance, no load test, and then more advanced testing like 10 delta, SFRA, etc., etc. Let's move on, because we are already almost, let's see, what is the time? 20 minutes past the set time. So the next question would be, what is the permissible limit value of partial discharge for transformers as per IEC? So once again, please don't look at the PD testing just as a number, because you are then very much limited. If you are testing in the factory, and if we are talking about the cast resin transformers, if I'm not mistaken, it is about 10, between 5 and 10 picocoulombs. That's the maximum value, but that's it is like, for example, try to imagine you have a spaceship, and inside of this spaceship you have all sorts of things like measurement instruments, sleeping quarters, and you also have a microwave, and everybody's focusing on microwave. How much time do I have to heat up my tea, and how much time do I have to put my beans in microwave to eat it? This is focusing on picocoulombs. This is just one aspect. Picocoulombs is just one aspect used in factory. When you measure in the field, use millivolts. The next question is, if PD value is in millivolts, how can I interpret in terms of Coulomb? So as mentioned before, if you are testing between 110 and 440 kilohertz according to IC 6270, there is a linear correlation between these two, and most of the testing equipment will automatically do this recalculation for you. The next question from Mr. Shahir, how can we calculate the winding value deviations, unbalanced values between phases? So I think that's the same question from before. I'm not sure what you mean by unbalanced values between phases, delta or star. Can you give me an example? It will be easier if you can send me an email, then I will have more time to look into that. A question from Mr. Hendricks, do you offer practical training in South Africa? Also, where can we obtain price lists for your products? In South Africa, we have a fantastic office. Doble has an office in South Africa with testing engineers, and yes, they do offer practical training. So just if you write down Doble South Africa in your Google search, you will find contacts. Mr. Raiben Naidru and Luendra Moodley are people who will probably answer your emails, and you can ask them for the prices of our products. Thank you, Mr. Reza, and some people have already left, which is understandable. Which is the broad-based test and which is the focused test? Mr. Raja, I'm not sure I understand. Please send me an email on that. Then we have another comment. I hope you will give another webinar with enough time to talk in detail about SFRA test. Well, thank you for suggestions like this, because then we know in which directions we should move. So yes, I also hope we can do something like this. The next question from Mr. Dimitros is, what is the proposed time interval for maintenance test and what test should we plan for? Well, proposed time would be, let's say, 3 years up to 5 years, not more than that, if the transformer is new and has no issues. If the transformer has issues, then it's less. If it has a lot of issues, you might need to test it every year. And if you don't want to test it every year, then every 2 years. It is like with a human being. If you are healthy, you will go for a regular checkup, maybe every 24 months or every 36 months. If you have some issues with your health, maybe you'll go to a doctor every month or every 3 months or every 4 months. There is no standard, but we have had a very good webinar and we will repeat it on asset health. That is the part of our that talks more about this. And the test which you will do, I would always start first with ratio test. I would also do winding resistance test as the last one. I would do a tan delta test, so that would be 3 of the basic tests, and I would do the oil test. With the oil, I would either send it to a lab or I would do an oil breakdown test, and these would be the basic tests. If there are some issues, I would also do the PD test and maybe SFRA if you have the results from the factory. And then these would be the basic tests which I would propose. The next question is, what are tests that need to be done to move the transformer from one location to another one, but within the same site? Do an SFRA test before and SFRA test after. That's my answer to that. Thank you to all of you who enjoyed this presentation. So I see some more questions. I hope a few more minutes and then we'll be done. Is the C2H4 gas increasing? What is the source? Well, it's always, in a sense, temperature. It's just the question how high the temperature was, and it can also be some sparking. But let me see if I can, Mr. Patel, if I can find more accurate data on that. Mr. Hatcher, what is the maximum percentage difference between winding resistance of windings? It is 2%, and in some cases 3%, not more than 3%. Now, it can depend on the voltage level of the transformer. If it's distribution, then 3%. If it's transmission, then 2%, but that would be the numbers. A question from Amal. We have a problem during filtration transformer. The oil showed too much bubble. The DGA show sign of gases. Electrical test is all good. How do we indicate where is the problem? Well, you first send the oil for a DGA analysis to understand which gases do you have, and then you start from that. Then I would do also the tan delta test and see what is wrong with my insulation. You might need also to change your oil. By that, I don't mean fully change the oil, but I mean to degas the oil. Acceptance criteria for the electric oil test. It depends on what is the voltage level at which you are running this oil. So it's always higher than the nominal value, but there is not one number for all, of course. And it also has different, according to different standards, we have IEEE and IEC standard. And just a few more questions and then we'll be done. Is it possible to have a failed winding resistance test and have a passed TTR test? Yeah, you can, because you can have a loose screw, which will show you the same ratio between primary and secondary, but you will have a bigger resistance. So that can very much happen. Can you show me how to test vector group of the transformer? Please download the presentation tomorrow. You have that. It's actually very simple. On the primary side, you always generate between phases A and B. And in the first test, on the secondary side, you measure, let me just mention that on the primary side, you will generate between phases A and B with phases B and C short-circuited, after which you will, in first test, measure between phases A and B, and in the second test, between phases A and C. And that should define the vector group with automatic test set. So this is with the automatic test set. For the manual one, the question is, the answer is a little bit longer. In on-site short circuit tests, sometimes the error compared to the nameplate is very high. Is it a measurement error since the test current is small? My answer would be yes, Luis. And my suggestion would be just take thicker cables on the secondary side. In most of the cases when I had a situation like this and when I connected on the secondary side the short circuit cables to thick short circuit cables, I will get a better result. For example, when you do a tan delta test, you can use a super thin wire. You can use a wire from the electronics on a tan delta test. But when you do a short circuit impedance, use as thick as possible cables on the secondary side. It will improve your testing result. Mr. Kuzu, transformer gas, there is a fault in the coil, but we can't find which one. Micrometers is nearly same. How can we find which coil is problematic? So we have a transformer and we have a fault in the coil. I would need more information. I mean, looking at this, it can be few things. But if you can, send me an email. A request to have more DGA and SFRA tests in the future. Okay, accepted. We will do that. Demagnetization is necessary before all tests. No. Demagnetization is not necessary. So if you do winding resistance last, you will actually need to do demagnetization only once. So effectively, you need to do demagnetization only after the winding resistance test, because it's something which saturates the core. And even if you do winding resistance right now, and then after that ratio test, it will not change the result, but it will change the result on SFRA and no load testing. So definitely before the SFRA test, if you've done winding resistance before that. Penultimate question, do we always need to perform PI, you mean, and DIR when doing the insulation resistance test? You don't need to do the PI if you did the DAR, and if the result is above 1. So then it is written basically in the presentation. The last question, why is it important to short circuit phases when performing C and TD measurement? Georgia, you have a good question. The reason why you do this is because you want to test the overall capacitance between the high voltage and the low voltage side, not the capacitance between phase A of the high voltage side and phase A of the low voltage side. This way you simplify the test execution and you actually create one point. So if you connect all three phases on high voltage side, then you have one point and it is called the high voltage. And if you do the same for the low voltage, then you have another point, which is the low voltage. So effectively you have 3 points: high voltage potential, low voltage potential, and the ground. And you measure capacitance between these 3 points: high voltage ground, low voltage ground, and high voltage low voltage. This is the standard because some wise people who have done many tests throughout the decades have decided that this is the best way. Of course, when you're doing the bushing test, then you can, but you don't have to remove the short circuit, because if you leave the short circuit, then you will just need to change the measurement from the tap adapter. But yeah, this is the answer to your question. It is basically the standard and it makes all the testing much quicker. If you would do it phase by phase, I honestly don't know what you would obtain, but then it would be more difficult to interpret the results. So where I am, it's 16:03. Thank you very much for your attention. You've been a great audience. Hope to see you again with the new webinar, which you will see very soon. Tomorrow you will get the PowerPoint, sorry, the PDF, also the recording. Don't forget to subscribe to our channel on YouTube. And once again, have a beautiful day. Goodbye.